Let's take a look at a mass spring system here to help clarify our definitions of our work kinetic energy theorem. Let's do the first condition where we do not have any friction. So that's condition 1. So we'll put a little number 1 here. No friction associated with this block system here. Okay, so I'm going to pull this block quickly, okay, such that I accelerate to a V final here. Okay, and I'm going to be stretching the spring at the same time, and we kind of want to look at what's going on here. So let's call the work I'm doing on this work external, EXT, because that's by my force applied external to the system. Okay, so you know what's really going to go on here? So well, we know that work net is going to go into the change, okay, in kinetic energy here, right? So it's this work net thing that's a little bit confusing here. So let's go ahead and deal with that. Okay, so what's really going on here? So I'm going to have a work external because I've got a force multiplied by distance by my hand. Okay, now the spring is being stretched, so energy is going into elastic potential energy. So I'm going to say plus a negative change to elastic potential energy. Okay, and that's going to go into the change in kinetic energy. So imagine me having like a force times distance here times the cosine of 0 plus a 1/2 kx squared, x being how far I've pulled this thing here. And that's going to go into a 1/2 mv squared. So let's go ahead and do that. So I'm going to go force, and I'm going to go times x. X is going to be, you know, a distance that I've actually stretched the spring. I'm using the letter x because that's what also is in our equation there. So then I'm going to go minus 1/2 kx squared is then going to equal, if I start from rest, our beginning velocity, of course, would be 0. But we're going to do 1/2 mv final squared minus 1/2 m times 0 squared. If I say that the beginning velocity was equal to 0 there. So I could find my final velocity if I know what my applied force was here and what my distance that I'm talking about. So remember, whatever x I apply here is going to be equal to how much I've stretched the spring. So that's how we can apply our work kinetic energy theorem. Now what about case number 2? There is actual friction. Okay, so in this case we have a box sliding here. We can ignore the friction in the spring. So of course we're going to have force normal mu is equal to our friction force. But down here I'm just going to call it friction force here. Okay, so let's go ahead and do this then. So what's our work net this time? So we're going to have a work external minus the work of friction, and you've got no choice there, that's always negative, plus a negative change in elastic potential energy, because again that's going to be going into elastic potential. We will not see that as kinetic energy. And then equals the change in kinetic energy here. Okay, so let's go ahead and do it again. So we're going to call that the force times x, and x being how much we have moved this object, minus force of friction multiplied by the same x, because that's how far we pulled it. Okay, minus 1/2 kx squared, because again that's going to be energy going into elastic potential, and we will not see that as kinetic energy, which then is equal to 1/2 mv final squared minus 1/2 m times 0 squared, if we're assuming that this does start from rest. So hopefully that, you know, kind of puts things in the perspective for you of how we apply these definitions of energy, and especially that, you know, work kinetic energy theorem. Now remember that conservative forces are the ones that do not include friction or any kind of thermal energy. So this first example here includes all things that are conservative. You know, the work done, the change in elastic potential energy and kinetic energies, all those are conservative. But down here we have one non-conservative, this friction work that's being done. That's energy loss to the system. It's not like it's destroyed, it's just going off as heat to the environment, and it's very hard to recover that and put that back into motion. So that's why we call that one a non-conservative. Okay, so there you go, and hopefully that helped to clarify things for you.